Welcome to the Deep Dive, the show where we slice through information overload to deliver the most impactful insights straight from the source. Today, we're diving to a topic that's, well, absolutely vital for anyone curious about uncovering digital secrets, exposing the truth in the digital evidence. Now, this deep dive is especially for you if you're a student at the Dr. Sam Pack College of Business, perhaps in management information systems, information technology, or computer information systems. And if computer forensics is your focus, then this foundational knowledge is really essential. But honestly, any college student, any working professional looking to understand how digital truth is actually found will get a lot out of this.
Absolutely. Our mission today really is to equip you with the core concepts about two fundamental operating system file structures, Linux and macOS. We'll peel back the layers, look at how data is organized, how it's stored, and crucially, how this understanding becomes, well, your investigative superpower in digital forensics.
Right. And all the insights we're sharing today come directly from Chapter 7 of Guide to Computer Forensics and Investigations by Nelson and Stewart. It's a foundational text in the field. Think of us as your guides, helping you navigate this powerful knowledge. And as we explore, please don't forget to like, subscribe, follow, share, and definitely comment with your thoughts and questions. We really do love hearing from you. Okay, so let's start with Linux. To really get a handle on its file systems, we kind of need to acknowledge its roots, right? UNIX, its predecessor, was designed from the ground up, actually, as a multi-user, multi-threaded, and secure operating system. What was it about UNIX, that made it so revolutionary that systems like Linux still build on it today?
That's a really good starting point. UNIX was groundbreaking because it solved a fundamental problem. How do you get multiple users working on the same system at the same time? Securely, efficiently. It introduced concepts like a hierarchical file system, consistent input-output, a really powerful command line interface, things that made it incredibly adaptable. Linux basically took those solid UNIX principles and made them open source, widely accessible. And that's why we see so many flavors of distributions today. The Linux kernel, that's the heart of the OS, it gets bundled with other software components to make a complete system.
Okay. And the source material, it highlights this clear evolution in Linux file systems. XTR2, then XT3 adding journaling, and now XT4. From a forensic investigator's perspective, what's the biggest jump there? Does XT4 give us new opportunities or maybe new challenges for evidence recovery compared to the older ones?
That's a key point. The introduction of journaling in XT3, that was a huge step for data integrity. Think of journaling as like a transaction log for the file system. It records changes before they're actually made. That makes recovery much more reliable if the system crashes. But XT4, which is pretty much the standard now for most Linux distributions, it really scales things up. It brought in support for partitions larger than 16 terabytes, much better management of huge files. For forensics, this means we're potentially dealing with exponentially larger data sets, which is both good and challenging. It demands more sophisticated tools, new ways of thinking about data carving and analysis. And when we talk about how XT4 actually structures itself, there are these four key components. They're like the blueprints. First, you got the boot block. This is where the initial bootstrap code lives, the very first instructions the system needs to, wake up. Next, the super block. Think of it as the file system's brain. It holds critical info about the whole file system, disk geometry. It's always tracking available space. It's fundamental metadata for any investigation.
Right, metadata.
Then there are inode blocks. These come right after the super block, and they essentially group together these things called inodes. We'll definitely talk more about those. And finally, the data blocks. These are the actual spots where your files and directories are stored on the disk drive.
Okay, inodes, you mentioned them. Why are these so central? What's the one thing about them that makes an investigator really pay attention?
Inodes. The key insight for forensics is that an inode is like a file's permanent record. It's a digital fingerprint that can stick around even if the file is deleted or renamed. An inode itself doesn't hold the data, but it's a direct pointer to that data. It's the map, even when the path looks messy.
A map to the data.
Exactly. When a file or directory is created, an inode gets assigned, and it contains all this essential metadata, like the mode and type of the file or directory, the number of links pointing to it, how many ways can you get to this file, the user ID, the group ID of the owner, UID and GID, the exact size in bytes, crucial timestamps, last access time, last modified time, and also the inode's own last status change time.
Okay, those timestamps sound critical.
They are. And fundamentally, the block addresses for the file data, including direct pointers, indirect, double indirect, even triple indirect pointers for handling really big fragmented files.
Wow, that's a ton of information packed in there. What's the maybe the trickiest part about pulling out or interpreting all that inode data in a real investigation?
It is dense, absolutely. And that snapshot of the file's life you get from the timestamps, it can be misleading if you don't understand exactly how they update or, if someone tried to tamper with the system. What's also fascinating and relevant here is how Linux uses different kinds of links. You have hard links. These are pointers that let you access the same file using different file names. But here's a key. These file names all point to the exact same inode and the same physical spot on the drive.
Okay, same in, same physical location.
Right. And an important detail for forensics, hard links must be on the same physical drive. The inode itself keeps track of how many hard links point to it in its link count field. You create them with the ln command, typically.
Sure.
And this really raises an important question for forensics. Understanding the difference between hard and symbolic links is vital. It's crucial when you're tracking down the true location and origin of data, because unlike hard links, symbolic links, sometimes called soft links, are just simple pointers to other files. They don't affect the original file's link count.
Ah, okay.
And this is a critical difference because a symbolic link, it can point to items on totally different drives or even somewhere else on the network. You make these with LNS. So for an investigator, knowing if something is a symbolic link or a hard link tells you a lot about where the actual data is stored and its potential connections.
That makes sense. Before we move off Linux completely, there's one more area mentioned that seems like it could hide secrets.
Right.
Bad blocks. What are these, and why should an investigator care about seemingly unusable parts of a disk?
Right, bad blocks. Basically, there's sections of a disk that have become unreliable. They can't reliably store data anymore. Usually it's just disk wear and tear. But forensically speaking, they matter because they can be exploited to hide information.
Hide information? How?
Well, if someone malicious identifies a bad block, they might try to manually store data there, hoping it won't show up with standard file system tools. Linux has tools like bad blocks, though you need root access for that, and also MK2S or E2Fseek, which can help find these areas. What's also useful for us is that Linux actually keeps a record of these bad sectors and a special bad block inode, so it potentially leaves another trail for us to follow.
Interesting. Okay, let's shift gears then. Let's talk macOS. Its file system has its own unique way of thinking about storage, right? Different terms, different structures. Historically, Mac systems use the hierarchical file system, HFS, and then HFS plus stan. And while Apple file system APFS is the newer standard introduced with macOS High Sierra, our deep dive today, based on the Nelson and Stewart text, is really focusing on those foundational HFS and HFS structures. Understanding these is still vital for many existing systems and, of course, for analyzing older evidence. And here's something crucial for investigators. In those older macOS versions, files actually had two distinct parts. You really need to grasp this split structure to know where different bits of information might live. There's the data fork, which holds the file's actual content, the text in your document, the pixels in an image, the raw data from an app, and then there's the resource fork. This stores file metadata and application-specific info, things like menus, dialog boxes, icons, maybe even executable code. This split means a file isn't just one chunk, which makes analysis a bit more nuanced.
That dual fork structure really is a key differentiator for older Macs.
And yet, when we talk about storage terms in macOS, they also have their own specific meanings. A volume, that's simple enough. It's any storage medium holding files. Could be the whole hard drive, could be just a partition. A logical block is a tiny piece of data, never more than 512 bytes. Indivisible, basically. Building on that, an allocation block is just a set of consecutive logical blocks grouped together.
Okay.
Now, to keep things running efficiently and stop data getting scattered all over the disk fragmentation, macOS uses something called clumps. Think of it like this. Instead of writing tiny bits of a file here and there, clumps group related data into larger, contiguous chunks. It makes reading and writing faster. And for us, sometimes it can make data recovery a little more straightforward if the blocks are together.
Right, contiguous blocks. Exactly. And finally, when you're looking at where a file actually ends, there are two end-of-file EOF descriptors. There's the logical EOF, which marks the real end of the file's data content. And then the physical EOF, which represents the total number of allocation blocks assigned to that file, even if they aren't all full.
Logical end versus physical space used. Got it.
Precisely. And beyond those, the macOS file system relies on several other key components to manage everything. Just like Linux, you have boot blocks for startup code. Then there's the master directory block, MDB, or volume information block, HIB, in HFS++. This is the central hub for all volume info. And cleverly, there's a backup copy stored near the end of the volume.
A backup, okay.
The volume control block, VCB, is like an active snapshot of info from the MDB that the file manager uses constantly. The extents overflow file is a helper. It helps the catalog manage file allocations when a file's data blocks are spread out too much for the main record. The catalog itself is central. It maintains all the relationships between files and directories. It's like the master index. The volume bitmap is a map, basically showing which blocks on the disk are used and which are free.
Like a visual allocation tracker.
You got it. And finally, there's the B tree. In macOS, this is a super efficient way to organize the directory hierarchy and file block mapping. Think of it like a self-sorting library catalog, structured like a tree. It lets the system find any file or directory incredibly quickly. For us in forensics, understanding this B tree structure is vital because it maps out the entire digital landscape of that Mac volume, shows us the connections. So if we connect all this back to the bigger picture, these structural differences, Linux versus Mac, they directly impact how you'd approach an investigation. For instance, just knowing where to look for user data. In Linux, you're typically going to home username and maybe root for the root user. But on a Mac, you're looking in user's username. And the root directories are different too. It's private air root.
That's a key difference. And you mentioned home exists on Mac, but is usually empty.
Exactly. It's there, but typically empty. That can trip you up if you're coming from Linux. Also, macOS generally has stricter access controls between user accounts. Users often can't easily see other users' files, and the guest account is usually off by default. These security defaults change how you might need to acquire or access data.
Right, those default settings matter. Now, when we talk about key macOS artifacts, where do application settings usually live? The source mentions PLIST files.
Yes, PLIST files, preference list files, often XML format, are very common for application settings. But you might also find settings in plain text files, or increasingly, stored within SQLite databases. And for security, you have FileVault. This encrypts a user's entire user's directory. FileVault 2 is the more recent version, which fixed some earlier security issues, but it also means encryption is more robust, making acquisition potentially harder if you don't have credentials or the right tools.
Okay, encryption is a big factor. What else?
Well, keychains are a huge artifact source. They've been around since macOS 8.6, managing passwords for apps, websites, Wi-Fi, system stuff.
Yeah.
If you need credentials, keychains are a primary target.
Definitely need to look there.
And on more modern macOS systems, unified logging is incredibly important. It creates these extensive logs. You'll find them mainly in Vard Diagnostics and vardbood.txt. And there are specific command line tools, log, show, that let examiners filter and analyze this data. They can be a goldmine for tracking activity.
Wow, okay. Now, acquiring an image from a Mac, it sounds like it can be physically challenging sometimes. You hear stories about needing special screwdrivers just to open a MacBook Air. What are some of these unique physical or logistical hurdles?
You're absolutely right. The physical access can be a real challenge. Getting drives out of modern Mac Minis, for example, often needs Apple-specific training just to avoid breaking things. And yes, MacBook Airs and other models often use proprietary pentalobe or Torx screws. You need the right tools.
So you can't just pop the drive out easily?
Not always, no. These physical barriers really underscore why you need a macOS-compatible forensic boot disk, a CD, DVD, or USB drive, to get a reliable image without altering the original evidence. This often means using specialized tools. BlackBag Technologies, for instance, makes MacQuisition, which is a bootable forensic imaging solution just for Macs. Sub Rosa Softmax Forensics Lab is another well-known one. It has a neat feature to disable or enable something called disk arbitration.
Disk arbitration.
Yeah, basically lets you connect a suspect Mac drive directly to your analysis Mac without needing an external hardware write blocker because the software handles the write protection. That could be really handy in the field.
That does sound useful. And once you have that raw image,
then many standard forensic suites can work with it. Tools like Guidance Software in Case, Recon macOS, X Forensics with Paladin, XOS Forensics, Access Data FTK, they can all analyze raw Mac images.
Good to know their options. Okay, let's circle back to Linux tools for a moment. They're obviously crucial too. The good news, the source says, is most commercial forensic tools can analyze various Linux file systems, ext2, 3, 4, even RiserFS.
That's true. And beyond the commercial tools, there are some incredibly powerful freeware options that are staples in the field. The Sleuth Kit, for example, it's a command line toolkit, very powerful, gives you deep control, a favorite for many. Then there's the Autopsy browser. This basically puts a web-based graphical interface on top of the Sleuth Kit, making it much more visual and maybe easier to use for analysis. But Importantly, you need Sleuth Kit installed first for Autopsy to work.
Okay, Sleuth Kit first, then Autopsy on top.
Right. And another great one is Foremost. It's a freeware carving tool. Foremost is excellent for pulling out specific file types, even if the file system structure is damaged or gone. It reads lots of image formats, and you can configure what it looks for using its foremost.conf file. Very handy.
Carving tools are essential.
Definitely. And you'll often hear the term tarball in the Linux world. It's just a way of bundling files and directories together into one compressed file, usually ending in .tar.gz or .tgz, common for backups or distributing software.
Right, a tarball. And what about getting a whole suite of these tools together?
Well, for that, Kali Linux is extremely popular. It's a Linux distribution specifically built for penetration testing and digital forensics. It comes preloaded with the Sleuth Kit, Foremost, Wireshark, Metasploit, just a huge collection of tools ready to go. A lot of practitioners use it, especially for field work or just having a dedicated forensic environment.
Makes sense. So wrapping things up a bit, we've really taken a deep dive today into these foundational file structures for Linux and macOS. We've looked at not just what they are, but how data gets organized, stored, and most importantly, how knowing this really empowers you in digital investigations. For anyone listening, especially our students at the Dr. Sam Pack College of Business, aiming to uncover digital truths. Grasping these underlying systems, it isn't just helpful. It's absolutely fundamental to being able to navigate and interpret digital evidence effectively.
Absolutely. And it leads to a forward-looking thought. Given how quickly operating systems and file systems evolve, think about cloud-native systems, edge computing, what challenges do you, the listener, foresee for computer forensics in the next, say, 5 to 10 years? How will investigators have to adapt as data storage and access continue to shift so dramatically?
That is a really powerful question to think about. Please share your thoughts, your predictions down in the comments section below. We'd love to see what you think. And while you're there, please don't forget to like, subscribe, follow, and share this deep dive. Share it with anyone else who might benefit from, becoming better informed in this fascinating world of digital forensics.
Thank you so much for joining us on this deep dive into exposing the truth in the digital evidence.
We really hope you gained some valuable insights today. Until next time.